From Rationalism to Materialism. This is a video based on a talk I'm going to give to the School of Materialist Research. The talk covers two topics, both against subjectivism. The first topic is something I've already had videos on, showing that the category subject, as used in philosophy, actually arises from the relations of production. It's not something in people's head. And I'm taking this on to look at how idealism held back or led to misconceptions as to how to do AI. Something which follows on from my previous videos is that conscious things and subjects are two different things. There are things that are subjects like Keir Starmer, British Petroleum, Bernard Arnault, L'Oreal, etc. A combination of human individuals and legal persons like firms, and there are things which are conscious, and the things which are conscious include human beings, but they certainly include dogs and parrots and other animals. We know that dogs are conscious because they become unconscious in the same way as we do when given anesthetic. Now, I'm going to be using this talk to illustrate Mao's thesis about where correct ideas come from, that they don't drop from the sky, they aren't innate in the mind, they only come from social practice, and in particular in this case the practice of production and the practice of scientific experiment. And I'm going to illustrate it that it was practice that led to correct ideas as to how thinking works, and how idealist apriorism led to a sidetrack. The whole business starts with a paper by Turing in 1950, where he says that in principle machines could think, and that, giving basically a very materialist analysis, that objections to this are unfounded. And he says that if a machine or other agent, non-human agent, behaves in a way that seems intelligent and interacts with us in an intelligent way, we should assume that they're thinking, because that's the only basis we have for assuming that other human beings are thinking. Now, he said that at the beginning of the 50s, AI started developing during the 50s and 60s, and it started off in what I'm calling a rationalist detour. It was influenced by debates in maths and logic that had happened in the first half of the 20th century. So, for instance, at MIT, McCarthy starts off with Church's lambda calculus and builds the programming language Lisp on top of that. And then for decades, most AI research in the US was based on Lisp. In Edinburgh, one of Miki, who was one of Turing's co-workers, goes to set up the School of Artificial Intelligence, and they are very much based on what they call expert systems, the collection of expert knowledge, and they develop various languages, Poplog, etc., to handle that. In Marseille, Colmar developed the language Prolog, which was very influential in European AI research from the 70s onwards. In the US, people were using things called Lisp machines, which were workstations optimized to run Lisp, and a couple of companies were producing these and did quite well during the period when there was a boom in the idea that you could do AI by Lisp. In Europe, the genealogy was coming from Boole, who had published his book The Laws of Thought. Now, nowadays we tend to think of Boole from the standpoint of the Boolean algebra used in computer hardware, but it was a philosophical concept of an algebra that he had, that he thought was the algebra of thought. And this then developed during the 19th century, early 20th century, with Frege, Russell, Whitehead, etc., coming down through Turing and Church for the lambda calculus. And then in the 60s, a guy called Robinson came up with algorithms by which you could deduce things from predicate logic. You could automatically deduce things from predicate logic. And Prolog built on all that. And it realized this dream of a calculus of thought, whereby logic could be directly transformed into executable code, and the resolution mechanism or unification mechanism allowed automated deduction. And it was thought this was what you needed for AI. A whole school of AI was built on this. There was a huge amount of investment went into it in the 80s. The Japanese launched what they called the fifth generation program, which it was said would produce machines capable of parallel processing, capable of understanding spoken language and understanding natural language. And all this was going to be achieved around the system of using Prolog and similar languages. In Britain, there was a similar program, the Alvey program, which built machines like Grip, Flagship, Alice. It all sank, all failed. Consigned to the bin of history. So much so that if you search the web for pictures, search Google Images for pictures of some of these machines built during that period, you can't find them. That's the only photo I could find of one of the machines built by the British Alvey program. It was such an embarrassing failure. Why did it fail? Well, it was based on idealist assumptions. It was based on the assumptions that thought could be modelled by a logic of truth values. Arguably, that goes right back to Aristotle, but it certainly was evident from Boole onwards. And that it builds up from a set of predicates that can be deductively chained, and if you can collect enough of these predicates in what in those days people were calling clause stores, then you can model the knowledge of human experts, and once you've done that, you've got artificial thought. Sounds fine. Except it was all idealist apriorism. It didn't work. As the Chinese were saying at the time, human knowledge originates and develops on the basis of social practice. Only through practice can truth be tested and developed with the fundamental aim of changing the world. No hero on earth can know and change the world when he departs from practice. This wasn't all based on practice. This was based on a priori assumptions that the brain operated in a logical, rational way. What was being ignored here was neuroscience. What neuroscience told us about how neurons actually work. An actual advance in AI depended on ideas of neurons being taken seriously and on techniques which arose from the struggle for production, and in particular such obscure things as computer graphics and information retrieval. So let's look at large language models. What are the key ideas or mechanisms on which they're based? Starts off with Hebb's idea of how the neuron works and how learning takes place by the strengthening of synaptic connections. It goes on to a guy called Salton, who in researching AI, information retrieval, comes up with vector space models of documents, saying that you can measure how similar an information retrieval query is to a document by using the cosine similarity measure. At the time, in the 80s, I was working for an information retrieval company, Memex, who were trying to do it all in hardware. And they were doing it all with Boolean logic and or not searching of documents. And they had a reasonable business for a while, but it wasn't the basis on which anything else was built in the long term. Dominic Widows has a book, The Geometry of Meaning, where he reports on research done at Google, where ideas of higher dimensional vector spaces are absolutely the key, so that information retrieval becomes a geometry problem, not a logic problem. Now, what's a cosine metric? Well, this is what's used when determining whether a query is similar to what it's retrieving. And if you have two vectors, A and B, you take the inner product of them, A dot B, and divide it by the product of the norms of the two vectors, the lengths of the vectors. So that's equivalent to normalizing the vectors so that they're on a unit hypersphere, and then taking the inner product of them. And this gives you the cosine, because if this is a unit hypersphere, A and B have been normalized so that they point along the unit hypersphere. The inner product operation measures the projection of one vector along another. And if we take the projection of A in the direction of B, we get this point A dot B, and by your elementary trigonometry you learned at school, that is the cosine of the angle between them. And, or at least it will be the cosine of the angle between them, because we know the distance A is 1. The point about that is it measures whether things are pointing in the same direction in word space. But the same thing can be done in semantic space. Are two things pointing in the same direction semantically? Or how? That's because as two things point in absolutely the same direction, the cosine becomes 1. If they point at right angles to one another, where they're orthogonal, the cosine becomes 0. Now this is actually very similar to what a neuron does. There's a neuron, set of dendrites, synapses at the end of an axon connecting to dendrites and other neurons. Well, the idealized model of a neuron proposed in the 50s was the perceptron, where you sum a series of incoming signals with these weights, weight 0 to weight n. The incoming signals are x0 to xn. You weight these, which correspond to the synaptic weights, sum them all, and then you feed it through a sigma function, which gives you an actual a psi function, which gives you a step output, 0, 1 output. Now, what's happening here is actually the same as an inner product operation. The inner product operation is the sum of the products of the elements, and this is the sum of the inputs and the weights. So what it's doing here is an inner product operation. So the key there is that neurons are working in a sense by inner product operations. And the underlying basis for nervous systems are these inner product operations going on. Now, just a reminder of what a matrix multiply does. If I feed in a vector B, a 6-element vector B, and we've got a 6x3 table here, matrix, we can perform the inner product of B with the first column to get C1, the second column to get C2, etc. So in general, a matrix gives you a way of mapping between vector spaces. It gives you a way of an n by m matrix gives you a way of mapping from an n inputs to m outputs. In this case, 6 inputs, 3 outputs. This is basically what Widows is doing at Google. He's saying you take in a vector of words, let's say these are words in your query, you put it through a transformation matrix, and you get a vector out, which is now a vector in semantic space, not in word space. It's a vector in the space of meanings. And you can then check similarities of meanings and get much better query performance than you could if you just searched on the words themselves. And it actually turns out that this idea of a semantic subspace is equivalent to what the neural net people had been coming up with when they proposed multi-layer perceptrons with a hidden layer, because they had already in the 60s shown that a simple perceptron, whilst it was very good at associating patterns, there were certain kinds of patterns it couldn't learn. The classic one being you can't get one to learn an XOR gate. But in the 80s, a book came out which had a big influence in reviving neural net research, which was a book by Parallel Distributed Processing by Rumelhart et al. And they gave several algorithms by which you can derive what should be the content or the weights of a hidden layer when training it on data. And this is essentially the same thing as trying to obtain the transformation matrix. I believe Widows does it by singular value decomposition rather than the kind of gradient descent techniques that are used in the neural net area. I asked DeepSeek that if we draw an analogy between the way it operates and the semantic space of Widows, what is the semantic vector space dimensions that you're operating with? And it said it's operating with a 4096 dimensional space. So we're dealing with very large matrix multipliers here, because the word vectors that you feed in have got to be larger than that, because there's more words in the language, and you have to take into account sliding windows for windows of attention. So these are very big matrix to vector multipliers that are involved at each step. And this is true both for query resolution at Google or AI systems. And it could only be done economically because hardware had developed GPUs which can do vector to matrix multiply efficiently. These are the Tesla cards which these big data centers use. They're optimized for fast linear algebra. But that grew out of NVIDIA cards which had been optimized for graphics. And why did you need it for graphics? It's because matrix to vector multiply underlies 3D graphics as well. If you want to project 3D points onto 2D space, you're starting off with a vector of 3 points in 3 dimensions. And if you want to rotate something, you want to scale it, all that can be encoded in a matrix, and you multiply all the points by these matrices, and you get what the stuff's going to look like on the screen. So GPUs were originally made to do these fast vector to matrix multiplies, and it then turned out you can use that for AI. So we had a confluence here. The idea that meaning was something handled in a higher dimensional space came from the practice of information retrieval. The ability to do large matrix to vector multiplies came from the practice of computer graphics building GPUs. And the idea that you can measure model thinking this way comes from neurology theory, perceptrons, etc. And these all feed together to create the large language models that we now have. So what I'm saying, the initial failure of AI, and its later success bears out the Chinese thesis that correct ideas come from practice. In this case, from the practice of experimental neuroscience, and plus the practice of information retrieval, which is part of the struggle for production, because information retrieval centers are one of the key branches of modern production.